Welcome to this explainer on the hidden geometry of data. I am absolutely thrilled to guide you through this today, because the concepts we're exploring, they are literally the invisible engines powering our modern digital world. I mean, from the dazzling computer graphics in your favorite games to the advanced machine learning architectures like GPT and transformers driving AI today, it all fundamentally relies on one simple yet incredibly powerful mathematical concept: the vector.
But that begs a pretty huge question, right? What exactly is a vector? Okay, let's dive into this. The fascinating thing here is if you pose this exact question to a room full of experts, your answer is going to depend entirely on whether you're asking a physicist or a computer scientist. It's almost like they're speaking two completely different dialects of the exact same mathematical language.
Section 1. 3 Perspectives on Vectors.
To really unpack this, we can look at a brilliant framework laid out by the mathematics channel 3 Blue 1 Brown. They break vectors down into distinct but deeply related perspectives. So look at the physics perspective on the left. Physics students view vectors as literal physical arrows pointing in space. What defines a given vector in that world is strictly its length and the direction it's pointing. You can pick that arrow up, move it anywhere in space, and boom, it's still the exact same vector. But on the right side, the computer science perspective operates completely differently. Computer scientists view vectors just as ordered lists of numbers representing data. No floating arrows in their code, just highly structured, ordered sequences of information.
Let's stick with that geometric physical view for just a second to build some intuition. In linear algebra, we prefer to anchor these physical arrows to a coordinate system. Basically, we're pinning their tail exactly at the origin, the 0, 0 mark. When we do that, the vector's magnitude is simply the specific length of that arrow. Think of it as representing the literal distance of a physical step, or movement in space, and its angle, that tells you the direction of that step. Anchoring the tail at the origin gives us this highly concrete visual way to understand movement, whether we're operating on a flat 2D plane or floating in 3D space.
Section 2. From Arrows to Data Feature Vectors. So how does drawing geometric arrows actually help us analyze complex information? Well, this brilliantly illustrates how the physical and digital worlds collide. Imagine you're a data analyst trying to predict the real estate market. For any given house, you probably care about two core features, right? The square footage and the price. You could write those two specific metrics down as a list, say $2,500 for the square footage and $500,000 for the price. In mathematical lingo, this ordered list of two numbers is literally a two-dimensional feature vector. We've successfully modeled a complex real-world concept as a purely mathematical object that a computer can easily digest.
And because our house data is now a mathematical object, we can actually perform operations on it, like vector addition. Geometrically, adding vectors is like taking sequential steps. You walk along the first vector, and where it ends, you place the tail of the second vector and just keep walking along that one. Your final destination, a new arrow drawn from the origin to your stopping point, is the sum of those vectors. But what does this mean for our computer science list? It is beautifully simple. To add vectors in a list, you just add the matching terms together. Top numbers add together, bottom numbers add together. The geometric motion maps perfectly, and I mean perfectly, to basic arithmetic.
The other fundamental vector operation you've got to know is scalar multiplication. Now, a scalar is just linear algebra's fancy word for a regular number. When you multiply a vector arrow by a scalar, you're effectively stretching the vector longer, squishing it shorter, or if you multiply by a negative number, reversing its direction entirely. And just like addition, this geometric stretching translates flawlessly to our computer science lists. Multiplying a vector by a scalar simply means you multiply every single numerical component in that ordered list by that exact same scalar number.
Section 3. Scaling up to high dimensions.
So far, we've really only been talking about two dimensions, like an x and y coordinate, or maybe three. But we're about to completely shatter that ceiling. 3072. I want you to let the sheer size of that number sink in for a second. We humans can really only visualize 3 dimensions. So what on earth does 3072 dimensions even represent? Well, in a famous machine learning dataset called CIFAR-10, researchers trained computers using tiny 32 by 32 pixel color images. When you calculate that 32 by 32 grid and multiply it by the 3 color channels, red, green, and blue, you get 3072. That means every single tiny image in this dataset is represented as one single point in a massive 3072-dimensional space. No way we can picture that, but the math still holds up perfectly.
Let's look closely at the pipeline of how this actually works, pulling from Stanford's CS231N course. See, computers don't look at a neat grid of pixels the way our human eyes do. To a computer, an image is just raw data. So the pipeline takes that 32 by 32 pixel image and it completely flattens it. It unrolls every single pixel's color value, stacking them one on top of the other into one continuous, incredibly long list. The final output is a single 3072 by 1 column vector. We have literally unspooled a two-dimensional image into a single high-dimensional vector so the machine can actually process it.
Section 4. Teaching computers to see.
Now that the image is a massive vector, we can use these vast lists of numbers to teach computers how to classify objects like cats, dogs, or ships. So the crucial point here is how a basic algorithm, like a linear classifier, processes these numbers. You can think of a linear classifier as a form of template matching. For every category it needs to learn, the algorithm creates a template vector. When you feed it a new, unknown image, it takes the image vector and the template vector and it compares them mathematically using an inner product or dot product. It's essentially multiplying their overlapping features to see how well they actually fit together.
Now, what's really interesting is what happens when the computer is just starting out and its templates or weights are completely wrong. Look at these scores. We fed the system a flattened vector of a cat image, but based on its current poorly tuned weights, it outputs a score for cat of -96.8, while giving the dog category a massive score of 437.9. The algorithm's vector math is completely convinced it's looking at a dog. The system is failing, and obviously it needs a way to know that it's failing.
Enter the loss function. A loss function is a strict mathematical formula that quantifies our exact level of unhappiness with the system's predictions on training data. When the computer's vector math produces the completely wrong classification, like confidently calling our cat a dog, the loss function acts as a numerical penalty. It evaluates those bad scores and generates a high loss value, basically yelling at the computer to adjust its weights and build a better template for the next round of training.
Let's see how this builds into two of the most popular loss functions used in machine learning today. On the left, we have the multi-class SVM, or support vector machine loss. The SVM is kinda laid back. It is perfectly happy and calculates zero loss as long as the score for the correct class is higher than all the incorrect classes by a specific, fixed margin. Once it clears that bar, the SVM stops worrying. But on the right, we have the softmax classifier. Softmax is way more demanding. It takes all those raw vector scores and squashes them into normalized probabilities between 0 and 1, ensuring they all add up to 100%. Softmax is never fully satisfied. It will keep tweaking the vectors, pushing the correct class closer and closer to a perfect probability of 1.
This incredible application of mapping images to categories brings our narrative full circle, returning to a brilliant quote from 3 Blue 1 Brown. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. The true magic of vectors isn't just in drawing physical arrows, and it isn't just in making massive lists of numbers. The true power lies in our ability to take visual geometric reality, translate it into crunchable computer numbers, and use that mathematical translation to teach machines how to comprehend the world. And hey, this doesn't just apply to computer vision. It is the exact same geometric magic powering large language models and transformers like GPT, where human language and words are transformed into these high-dimensional feature vectors so AI can actually understand us.
Which leaves us with this final, profound thought. Before a computer can understand anything about our world, everything must first become a vector. So, I want you to take a second and just look around the room you're sitting in right now. Look at the colors, the lighting, the shapes of the objects around you. What sequence of numbers would perfectly represent your world? Thank you so much for joining me on this explainer, and remember, keep looking for the hidden geometry everywhere.